Ladies and gentlemen, welcome to Untitled Science. So far we have come a long way to reach where we are now. So we have done, we have read BIP text data in R, and then after we read the BIP text data, we have done some bibliometric analysis, and then after bibliometric analysis, we have done some text analysis using tidy text, and then after that we have done text analysis, text preprocessing using quantida, and then from there we have moved to text classification, and we have already implemented Bayesian classification in support vector machines, linear SVM actually in quantida text modules package, and then last time on the part 16 of the video series that I'm currently doing, we have done some quick SVM using the ETN71 package. But today I would like to go further in training support vector machine, and I would like to do the tuning. So you have to tune support vector machines to identify the optimal parameters for your algorithm, for your support vector machine algorithm. So if you remember last time, we have done some converting the document feature matrix. So as I said last time, so you know, when you do quantida text analysis, quantida, it gives you file formats called document feature matrix. So sometimes if you are implementing other algorithms outside of quantida text modules, you may have to convert this document feature matrix into the data frame, because in R, you know, many of the algorithms, many of the models, they usually like to have document feature, data frame instead of document feature matrix. The good thing with quantida is it offers you another function called convert. So it gives you this function, so you can convert this document feature matrix objects into a data frame using this simple, very short line, of course. So you can use convert, and then you give it your document feature matrix, and after that you have to give the data frame. So you say to data frame, from which are you converting? It's from document feature matrix, and you are going to convert it to data frame. So once you convert that, the first thing you have to do is you have to investigate your you have to look how your variables are structured. So in document feature matrix, when you first convert it, so you will have additional variable on top. So that's why we decided to remove. We have to remove that variable because it's a row name. So the name of the rows, that doc ID from our quantida text analysis, if you remember. So we were doing this doc ID, and that doc ID was part of our feature. So that's why we had removed this variable. But the main goal of this file conversion changing document feature matrix into a data frame is just because we may implement further new algorithms in the coming series. So we have to make sure that you have to know that it's possible to convert document feature matrix into a data frame. And last time we have also done this quick SVM training using this syntax. So we first take the x and the y variable, and after that we have done this SVM. So we use SVM and x equal x. So because we already x is train data frame, all the features, all of these features. So I mean, if you look at these features, they actually most of them are 0, which is actually that the term is not present in this particular document, and some of the terms maybe let's say this one pandemic has two times. It was mentioned 2 times in this abstract, but most of the terms they mostly have this like 0, 1, those kind of terms. So at least the ones with 0, I mean, this kind of data is called very sparse. Sparse. It's really sparse. So sometimes you may, depending on how large is your data set. So sometimes if you have really long many rows, and then at the same time you have a large number of features, then you will have problem because your model may have difficulties when training. So I mean difficulties in a sense it will take a really long time. So for that you may need to use this function called DFM trim, so that it will give you you can remove with this DFM trim. You can remove like terms that are not that have zero cells in like 95% of the document, or 97, 98 or something. You can simply create your own threshold to remove those documents, and you can simply use this DFM trim. So once you trim and remove the sparse features, you can simply convert it to TF-IDF as we have done in the previous session. Or I'd suggest to look at quantida again. It has so many powerful functions. But for today I will just proceed to the tuning. So for tuning, let me just remind one thing. So that is SVM. Let's look at what SVM actually requires. So SVM, when you train SVM, the first thing we have to do is x and y variable, and then we choose kernel choice, and then we give it the gamma parameters. We were giving like gamma. Actually, gamma you don't need it if linear. If your kernel choice is linear, then you don't need gamma parameter. And the other most important parameter is cost. Cost actually you need it for all kernels. Actually, what the gamma parameter does is you can have a look at actually from the details. This scikit-learn from Python, they have better explanation than the ETN71 explanation. I mean, you may find tons of materials, others, but I found the scikit-learn explanation for gamma and cost parameters much better than the ETN71. So you might also look what gamma and cost parameters are. Actually, what gamma does is how far in your support vector machine, because your goal is to find the optimum decision boundary. So in your optimum decision boundary, if you remember where your line should be, so in that line and the gamma parameter controls how far should the margin, I mean how far should the influence of those support vectors of the training, the dots or the those training examples, and how far they have to be from the margin. That's what the gamma parameter controls. So if you assign a large gamma parameter, then it tells the algorithm that the decision boundary can do some kind of zigzagging, to take on some of the points, the training examples. But if you give it a small value, then you are giving it a lower weight. That's what it has. And the cost parameter is controlling the trade-off between the decision boundary and the classification points, the classifying points. So high cost means, again, it's pushing the decision boundary away from the classification points. But your goal is, again, to maximize the decision boundary. You can find tons of better explanations. I will not go much in detail into explaining the parameters of SVM. So to tune SVM, the function that you need is this tune. So you can use tune, and then let me have a look what tune actually has. So what it needs. So it needs a tune. It needs a method, which is because it's tune function from E1071. It defines, it also does for other models like NiBi, ScaleNN, and other algorithms. I think they have also included additional models. So you define the method, and the method is SVM, and then same train X, you give the train X, and the train Y. So the train X is all the document feature matrix, and the train Y is our train include, and then you give like validation set, like the X validation, cross validation. So you give it a cross validation, and the validation Y is if you give it I mean, if you just define validation X, that's fine. But if you already have your own validation dataset, then you can also define it. Otherwise, if you define validation X, you don't need to define validation Y, because the SVM algorithm can by default take it from your training data. And then after that, you can give a tune control. We will come back to that point. And these are the main things. So since the method is SVM, is going to be SVM, make sure that in your object, in the list of objects that you created in your in your R environment, in R Studio environment or something, you should not have an object called SVM. Otherwise, you're gonna have a problem. So I mean, you don't need to name your algorithm SVM or something, SVM like this. So you don't like tune or something. You should not give this kind of name. Otherwise, you will have a problem. Just like that, you don't need to like data frame. Let's say if you usually it's not recommended to your data frame. You should not name it a data or something, because there are other functions within R that say data. So then you should not name. So in case, to make sure that you don't have this SVM object, you use RM, which means remove. So if you have any SVM objects, then you have to remove it. So you can remove it, and then I don't have it, but make sure before tuning your SVM algorithm, you just have to remove that SVM object. Yeah, so now I will proceed directly to tuning SVM. So the first thing is we need to do is we have already loaded our library, 1071, so we don't worry about loading the library. And then first thing I need to do is I need to assign starting time, because I want to control how much time it takes. System time. So system time, it tells you the current time, and then the last one would be time minus, because a start time already we assign it. So start time minus, again, system time. So the system time at the last point will be different. So then you will have the time, how long it took to train this algorithm. Let me give it a name called SVM tuned. SVM tuned radial. Let me call it radial like this, and then let me use this tune function. As I said, the tune function requires the first thing is the method. The method is SVM, so we don't need to define anything else. And then after that, the second parameter is train X. Train X is our. You can use a data frame, but depending on your I mean, for me, I don't have to define. I don't have to convert the document feature matrix to use SVM. But sometimes you may have that problem. If you have that problem, then you have to convert that data frame. I mean, that document feature matrix into a data frame. So our train X is all document feature matrix. So that's document feature matrix, and then the train Y would be train include, but it should be. You should make sure that you have to save it as fact. So you may have to make sure this train. Where is that $sign? Okay, here it is. So train include, that's our train Y and train X. Then the second one is the kernel. We have to define our kernel parameter, and then let me use, because I'm using radial, so I'm defining my kernel to be radial. Then the next one is, let me define the type. I think by default it's classification, but if you are doing regression, you have to define again classification. Otherwise, I think it's optional, but you need to make sure that it's classification. Then after that, you can parallelize. So you can parallelize in a sense. So because you are doing cross validation, tenfold cross validation, then it can run all the calculations in parallel, and then at the end it will combine all of them. Yeah, it sounds a fancy idea. I have no idea how it, it finally combines all of them, but that's how it's yeah. So parallel, and then finally there is another parameter called ranges, and for the ranges you can do is you can use a list, because here we want to define cost and gamma. These are the two things that we want to define here. So we need cost, and then we need the gamma. So here you can kind of use this sequence function, and then let's say from 0.001 to let's say 0.1, maybe 5, and then with the step function would be let's say I don't know, 0.1 or something. So you can use this kind of let's say if you use probably you know about this sequence. So let's say if you say sequence 2 to 9, and then let's say 5 3, so that means the step is a 3. So the 2, and then the next one would be 5, and the third one would be 8. So it's no, SEQ. So if I run this, so you see it's 2 first, and then 5, and then 8. And if you also do this to I don't know 10, no, 18 for example, so it's jumping every 3. So that's how it's same is true. You can do this sequence, but I will just do my own choices instead. So I will use simply concatenated, and I will simply use these values, cost, and then I simply use this different values. So the first one is 0.01. You can kind of do from 0.01 to 15 with a step function, like this, what we did. But I just want to try only this ones. I mean, it depends how powerful is your PC. That's what it is. And then for the gamma also, this is for the cost. You can basically write from 0 to 100, or maybe more. I don't know. But the larger the value it is, then the more your decision boundary will be pushed, will be forced to include more support vectors. I think the number of support vectors will be larger if you really have put your cost parameter to be larger than 100. But for the gamma, again, we need parameters, but you can define it again using this as a sequence SEQ function. But I will just simply use my own list instead of jumping or something. I'll just use this one. So let me drop this here, and then after that I will define another parameter. Since I mentioned, yeah, that's the wrong bracket, so I don't have to type it twice. So now it should be here, and then the next parameter is this validation X. That's the cross validation. Validation X. It seems my Anaconda is not predicting it. Let me check again. Validation X. Okay, validation X. For the validation X, you can use again tune control. If you know Caret package, they have also train control. Train control, I think, where you can define your cross validation and repeated cross validation or tenfold cross validation or something. So, but SVM algorithm, they have already written the validation X function for us, so we don't need to worry about train control in Caret. In fact, I was trying to implement an SVM using Caret, and I found it incredibly very slow. I mean, incredibly slow. Then that's why I switched, simply following the tuning algorithm using just the E1071 package. Then this is the first thing, tune control. And the first thing we need is sampling. So you need to define sampling. The sampling, we are using cross validation, but you can also use repeated cross validation. So that we are using just cross validation. Repeated is like, let's say if you use repeat 3 times, that means tenfold cross validation repeated 3 times, which will make your training very, very slow, extremely slow actually. And then after that, you define the cross value, and that cross value is tenfold cross validation. After that, we are done. We just need to close our bracket. We close the bracket, and then we should be ready to run. So now I will run it, and I will I will stop I will pause the video and come back after it's completed. Let me define again another one, actually, not only for this one, because we want 2 models. One is for SVM radial using train document feature matrix, and the other one would be using for the TF idea. And I also forgot another thing. I need to make sure that because we are using cross validation, tenfold cross validation, and there is sampling. So whenever there is sampling, you make sure that your results are reproducible. So make sure to use setseed. Setseed function actually controls you. That's mainly for reproducibility. So it's just to make your results reproducible, so that every time the sampling will be the same, so it will not change, because you fixed it. Otherwise, if you don't use it setseed, the sampling will be different. So that's why you need to make sure that you have defined this setseed. Once now we are all done, we are all set. Before we run it, let me bring this up, and I copy the whole thing again, and then so later we will have 2 times, like one for the For this one, let me copy the whole thing from start time again. Then I will simply change a few things for the, let me copy it and maybe put it here again. And now let me call this one TF-IDF, and I'm going to use a TF-IDF version of the data. That's all. And the rest of it will stay the same because I am using a different version of the data. Otherwise, I just want to compare how whether this is using the TF-IDF version and the other one TF-IDF actually, and the other one is using the simple frequency. Simple frequency, in a sense, words are simply counted, the number of times a word is mentioned in a document. So that's what document feature matrix, our document feature matrix data looks like. But actually, we can actually have a look how the train. Let me just train TF-mat document feature matrix. This is how it looks like. So it's simply the number of times a word is counted in a document. These are the identifiers, the doc IDs. If you remember, in our data frame also we had this, but finally we removed it. And then yeah, these are simply the number of times a word appeared in a document. But when you take it to TF-IDF, then it's a different because they are weighted. I have another video on TF-IDF, so you can go back and revise yourself how you can calculate the TF-IDF. So these are weighted. So if you remember, the previous ones are simply discrete numbers like 1, 2, 3, 4, 5, 6 or something. But here they are weighted by number of times are mentioned in a document, and depending on the number of documents you have. So that's a key difference. And we want to see whether using TF-IDF actually makes a difference in your training. So later we will say. Well, using TF-IDF version of the data is more sensitive or specific or more accurate, things like that. So now I will run the whole thing. Then I will wait how long this will take. Yeah, let me pause the video and we'll come back. Yes, now the algorithm is training is completed. So the first algorithm, the document feature matrix, it took only about 10 minutes to complete the whole training, and the second one took about 12 minutes. This is how much time it took to train the models. So now we have already the models. We already have the models, and we can have a look how our models look like. So let me just bring this and then see how they look like actually. So let me see. Let me actually add few cells. So this one is telling this is if I simply print the whole object. Actually, let me start from the simple frequency model, and this it tells me these are the best model performance, and this tenfold cross validation, and we have cost gamma values. And but again, the best way to do is you can do a summary. So just like other regression models, you can use a summary function and print your summary of your model. So here we have tenfold cross validation. That's and the best parameter is the cost is at 5 and the gamma value is at 0.0 something, at a really tiny value. Then and then the best performance is like this is where it is. And then you have all, because we have different combination of cost, gamma, error, and dispersion. These are all the while tuning, it's calculating the error. So at the end, the decision or the choice of the best model is based on the error. So the model that has the smallest error will be our preferred model, our optimal classifier. And you can also check names, what this object has. This object will come up with many of these models. So if you have best parameters, best performance method, and so on and so forth. So you can simply take again and print, see what are the best parameters. So let's say you can say, okay, these are the best parameters. Here are my best parameters, just like it was also printed in the summary of the model. But you can also see what is my best model. Let's say again, best model. And here are the best models. So again, it's 356 support vectors. Quite impressive. It's much lower than the total number of training examples. If you remember, the total number of training examples is in team. Let me just say, I think I have train df. Let me just team df mat. No, train df. Let me just check train df. It's the same number of rows. So I have 689 training examples, like number of training dataset or training example, you can call it, and I have only 356 support vectors. It's kind of much lower than. Yeah, I mean, you can do better if this number is lower. Yeah, but it seems it's a good sign that it's much lower. Yeah, but now we have our model. So the next thing is to use this model for prediction. Yeah, actually, since we have our model, if you remember, let me just go back. And so we have all this, we go again, summary. I just want to say something for probably for the next video or something. So you know, I have different values. So these are the cost and gamma and the dispersion values and all the combination. So it's combining 0.01 with 0.09 and it's getting this number of error. So let me finally, I mean, what we need is we can export this data into a data frame, and then we can use it for plotting. We can use it for plotting, and I can show you where actually this value, this combination, and we can use ggplot2 and replot this data. But we haven't reached to that. I just want now. I just want to use the prediction. I want to use it for prediction. So for pred, let me just svm radial, and then the first thing you need is a predict function, and then after that you can svm tuned. You can give your model. So I have svm tuned radial. That's my model. So in predict function, the first argument is model, and the second argument is new data. So we have our new data is, if you remember, we have this matched data frame, matched df mat. So now we can run this. So it seems I made a mistake here somewhere. So no applicable method for predict. Yeah. So you know, because this model, it has many models. I mean, so it is because it's tuned, it has lots of models. I mean, let me say because it only needs this best model, the best model. So I need to choose the best model instead of giving it all different names. Let me just use these names and check how many. I mean, what kind of names we have. So I have best model. So I need to check the best model. So I just need to choose this and put it here. So then I am choosing the right model for prediction. So SVM. Now you state best model, actually best model. Actually, it should. My Anaconda is not. It's not doing well today. Or yeah. So SVM radial. It's removing it. Yeah. Okay. Best model. So now I choose the best model for prediction, and I give it my my test data frame. Now it should work. Now it's already done. Let me just, if you want table, then we can use pred SVM. I think pred SVM. That's what. Okay, this is pred SVM radial. That's what we did. Pred SVM radial. So we already have like 155 of the 300 something documents were classified as COVID, and the other ones as SARS. But you can also add the train include, and then you can have the 2x2 table. No, I'm not using the train. Instead, it should be test. Sorry, otherwise it will not match. So now it looks it has worked really well. So 145 of these are the predictions, and these are the on my model. These are the predictions, the pred, and these are the gold standard. I mean, that's when they are labeled. So that means 145 of them were correctly labeled as COVID, and 131 of them were correctly labeled as SARS. Then you can simply pass again confusion matrix function here, and then you can see the whole thing here. And then we can define the mode, everything, and so everything will be printed out. Everything. Yeah, now it shows, it's impressive, isn't it? So you have an accuracy of 93% and a sensitivity of 95%, a specificity of 92%, and impressively the precision is again 94%. This is really awesome. This is really great. And maybe let me check again how this worked for the TF-IDF version of our model. And mind you, it reminds these numbers 93.88 and 94.7, 95%. And let me see and how it works. Okay, I made a mistake here. So let me just TF-IDF, now it should work. And let me just check again. Here we have missed, I mean, it worked well in terms of predicting correctly the SARS, but it has lost something. So instead, so that's why our accuracy is much lower. So that means the TF-IDF didn't, I mean, it's impressive. It has worked well, especially in terms of identifying the negative documents, SARS, instead of detecting the positive documents. But that seems to be not working well. Yeah, but instead of doing this, let me show you. I mean, if you want to save, actually you can save it like this. And the next one, I can also let me remove this TF-IDF, and instead create two objectives for the SVM trail. And let me call this one because it's coming from the TF-IDF version of the model. And let me give it this TF-IDF. And now let me give it again. This is TF-IDF version of the model. Let me bring this one. I think I made an error in the previous version because I was using the TF-IDF, the model that was trained using TF-IDF version of the model, and I passed this data frame to the TF-IDF. I don't know whether that makes much difference, but let me run and see it. And let me see this TF-IDF version. And let me see. Let's see. Yeah, it seems it's different. So it's that was 84%. Now it's 87% when I plug in the right kind of data. Yeah. So that's how you can do. So this you can save these objectives, but let me show you something better. less functional approach. So let me create a function called predconf. Predconf is like prediction and confidence prediction confusion matrix. Let me call it just predconf, or predconf. Actually, this should be okay. Predconf, and then I can simply create a function, and this function should take a trained model. Because we can use this function many times. So the trained model, it uses trained model, and then the test data. So it should use the test data, the trained model, and the test data. After that, you take these curly braces, and let me define the predict class. Predict class, and then predict class. That the way you do predict is you can use a predict function, predict, and then what you do is your best trained model, and then okay, I'm doing an error here, and then you give your test data. Okay, it's fast. Okay, and then the next thing I want to do is I want to tabulate them. I want to tabulated class. Let me tabulate them. And to tabulate, you can simply make a table of the pred class, this predict class, and then the test data, test include, or let me just use the original data actually, test include, or you can define it somewhere that X is test include or something. Let me just use this one because I'm using this test data everywhere in many of my algorithms, so I can simply define it this way. And then once you have that, let me create the confusion matrix, confmat. Let me just do this, confmat actually, let me call it confmat, and then this confmat should work confusion matrix. That's what I need. And then the confusion matrix should take the tabulated class, and then in the mode should be everything. Yeah, everything. Now I have everything. The next thing is I need to return my objectives so that they will be displayed. So the first thing that I need is confmat confusion matrix that I already defined above, and then I want to again maybe print tablet class. I don't want to print all of this, the pred class, because they will be large for all 600 and 300 something documents. They will be listed in my output, so I don't want to print this one. Instead, I want to print the tablet class and the confusion matrix. But in R, the return function doesn't like to have like this, like two objectives. You can return them twice, but otherwise it doesn't return multiple objectives. To return multiple objectives, we can pass the list argument with the list function here, and then we will not have any problem. So that's what we need. Now we have already our own function, and then every time we don't have to use predict. We don't have to run everything to print. Yeah, so we just need to define this one, and then we can rule them with this function. Let me run this function, and then after that, let me just use pred class conf, and then predconf. I use my best model is, let's say, SVN. My best model is SVN radial, and then this model, that's my best model. Then my training data is my test data is dfmat. If you remember, it's this one is my training data. So let me just do this, and then let me check dfmat, and now it should be able to run my model. I don't just made an error. Now test included, not included, should be include. So I made another error. So let me run again. Now it's working. So now I have my function returned two objectives. Two of my objects. The first object is a confusion matrix, or the contingency table. It is 2 by 2 table, and then the second one is a confusion matrix, and it's giving me my the whole values for this confusion matrix, including the 95% confidence interval for accuracy. In fact, you can also calculate confidence intervals for these ones. Maybe in the future I can show you how you can calculate confidence intervals using easy functions. And again, let me do another one for the TF-IDF version of my model. So let me just use TF-IDF, and again here I plug in my TF-IDF version of the data, then run it and see how much they are different. So let's say here, so you see I have my accuracy is 89%, and sensitivity is 87%, and specificity 90%. Whereas in the previous, in the first round of my data, I have this impressive 95% sensitivity and accuracy of 94%. In fact, if you look at these values, I mean, the good thing I have is my data is a well-balanced data set. So whenever you have imbalanced data set, you need to make sure to do balancing strategies. Maybe in the future, I can also show you how to balance, how to make like up sampling, down sampling. But for this purpose, I purposely chosen a fairly balanced data set. Yeah, so it looks very impressive. So in the next, maybe in the next one, I will train another. Let me see how long it is. Yeah, oh, that's 43 minutes. So, yeah, okay. So, yeah, so this is how you can. Maybe I can check the other one. The other one would be on linear. Okay, so now we have already trained a radial basis function using support vector machine, and we have seen radial SVM, and it seems it has worked very well. So now the next thing is I want to try how linear or sigmoid or polynomial kind of support vector machine would make a difference in your prediction. So now let me create a few more cells and let me pass this, and then I will rename these objects into SVM linear and things like that. So to do that, what I need is I just need to define this radial into linear. I will call it linear, and then this one again linear, and then I will define this, make it linear. Again, I will again define this linear. But as I said, the linear SVM doesn't need a gamma parameter, so you can't remove this one from your syntax. Again, here you can't remove this gamma parameter from your list. So you have already defined linear SVM linear tuned linear TF-IDF, again SVM tuned linear TF-IDF. Now we have crossbar. The rest will be the same. So SVM doesn't, linear SVM doesn't want like a gamma parameter. That's what I mean. If you keep it, it will ignore it. Your parameters will be ignored. The one you set, they will be ignored, and still by default it will take the 0. I'm simply ignoring it. But it's nicer if you just not include the gamma parameter in your linear SVM. So again, I will run this again for some time and come back in a minute when it's completed. Yeah, welcome back. It's now completed. So the first one, it actually didn't take long. The first one, the non-TF-IDF version of the model, it took only 44 seconds, but the other one with TF-IDF version of the data, it took only 1.2 minutes. This is relatively faster because we didn't have gamma parameters, so there will not be many combinations and the like. So the second thing that I want to do here is I want to predict and I want to print my confusion matrix. So let me just use pred class, but pred linear, maybe linear SVM. Let me call it linear SVM. And then after that, as I said, what I need is I need to use the predict function. And then with the predict function, the best thing I want to use is SVM linear, my SVM linear model. This is here, and then SVM linear, then base model. That's my base model. Here is my base model, and then after that I need to define the new data. My new data is what is it called? This matched TF math. Then let me again do the same for TF-IDF version of the data, because I will use these predictions later if I want to like calculate cones, not really cones kappa, but the other kappa, which is for multiple raters, because I want to combine all these predictions, and you can create this kappa value. I don't know if there was one name called, I just forget the name of that kappa. It's a kappa that you use for multiple raters. The cones kappa is usually for 2, but for more than 3 you need another kappa. I just can't find it. I have used it, but I will also show you how to do it. And then base model. So we have already our base model, and then we give the TF-IDF version of our data, TF-math, TF-IDF. Now it should be working. Let me change this to again here another error. After that, I can simply run, and it's really fast. It's already completed. So then next thing I can use my pred conf function, the function that I created above, and then for that what I use is I simply give my test data. Actually, I can, so new data, it's test data that I use, I think from my parameters of my pred function, this test data. So test data, I can use test data equals, and then let me run it. How this works, actually I can also print the other one. Let me print again. This one will be linear SVM, TF-IDF, and then this one will be my TF-IDF version of the data. Otherwise, everything will stay the same, and run it. Now I have, again, another impressive algorithm, which seems to be working very well. That's a linear SVM, but it still didn't beat radial SVM. So it's 93% accuracy. 93% accuracy and 93.5 actually sensitivity, and about 93% specificity, which seems again very impressive. And again, for the TF-IDF version, so we have lost something in specificity here in terms of detecting the negative values. That's why our specificity should be but the sensitivity is it's identical actually from the previous one. Again, the specificity is a little bit down, but otherwise, again, these models are quite impressive. You may not have this kind of performance in, I don't know, in the real world setting, but I found this thing, especially if you have a really imbalanced data or something, you may not achieve this kind of performance. But otherwise, it seems to me really impressive performance with these support vector machine models. Yeah, so The next one, if you want, you can change things to sigmoid or polynomial. Probably sigmoid may work better. Otherwise, this is how you train it. And a polynomial, again, I have tried polynomial, and it really doesn't make much sense in text data. I don't know. I have tried it many times, and I have seen good performance from from sigmoid. I mean from polynomial kernel. But sigmoid is another good kernel choice. So you may try that. But for now, I will not do another tuning. But this is how the tuning SVM in E1071 looks like. We can kind of maybe in the next video I can extract the values of those. When I print. If you remember, I was printing this summary. Let me show you summary like this SVM linear. So you have all these parameters. So I can take the cost and the error, and I can show you where is the lowest error. So it's telling me that 0.01 is where my lowest error, but still when you look at the errors, there are still more errors. I mean, if I add more values here, like more cost parameters, like if I because it seems the best parameter is when the cost value is really smaller. So if you remember here, down here the cost is 0.01. Probably if I remove these ones and add more points on this, then on this side of the cost parameter, I mean cost values, then probably my linear SVM may improve. Otherwise, I can drop these ones, this part of the graph, because it doesn't make much change to add all of these values, and instead work more on adding more values between 0.01 and 0.05. Probably that makes my model, my linear SVM, better than maybe it will be able to beat a radial SVM. Otherwise, it seems quite impressive to me that we have managed to reach this 93% performance. Yeah. Having said that, that's how tuning SVM looks like. Enjoy support vector machines. Thank you.